So this is my transformer playlist, and on the very first video of the transformer playlist I will go through on the whole architecture of the transformer model itself, and in the later video I will go through in depth on individual component of the transformer architecture. So in the beginning, an input text is fed on the transformer architecture transformer model, but in order for the transformer model to understand the natural language sentences or text, they need to be preprocessed. So for instance, if there's an input text something like the quick brown fox, they'll be tokenized into smaller chunks. So here, like the there are many different methods to tokenize input text. So one of them is byte pair encoding. So in byte pair encoding, of the words are chunked into even more granular level. For instance, like geology can be chunked into geo and logi, and because logi the chunk logi is used repeatedly in different words, and geo can be used in different words as part of different words. So they are tokenized so that they can be used repeatedly in different words using the same representation. So after the tokenization of the input, they are mapped into some tokenized IDs, and those ID will be correspond to some vectors, part vectors. And so initially there are some word embeddings, or each of the words they're represented by some word vector, and they are going to be each of the word is going to be live in some n-dimensional vector, and the position on the n-dimensional space will represent some of the properties of the word and their relation with other words within the space. So for instance, that king and queen, both of the words are related on this space, and as both of them have the same properties, sometimes, like by adding or subtracting the property of female, the word female, word presentation of the female presentation of the word vector, we can get queen by subtracting it from the king. So after the word embeddings, we need to add positional encodings to the input text, because when it's in the in the predecessor of the transformer architecture, we had RNN, LSTM, GRU. All of them used to have input text in sequentially. So by doing that, we could capture the sequential nature of the input text, but doing so, the processing and the training and inferencing, everything would be slowed down because of the sequential nature of the architectures. So because transformer is try to bring parallelization into the table. We It had to, like, transformer process all the input text all at once. It loses the words themselves, loses their sequential nature within the transformer model in the time of training and in the time of inference. So that's why we need to add additional information of the word's position using positional encodings. So positional encodings will be added to each of the word vector, and they will capture the position within the sentence of the word. So after adding with word positional encodings with the word embeddings, we can get the enriched encodings, and from there will be some linear transformations for to normalize the input vectors, and after that there will be some multiplication of the with the English encodings, in English encodings. So there will be word in word embedding, with the word embedding there will be one multiplication with the weight matrix of query, and another weight matrix of keys, and another weight matrix of values. So we'll get three different matrices. One of them will be in time, in dimensional, like all three of them will be in dimension, n times d model dimensional. So uh, so if the query space, key space, and value space will be much smaller than the word embedding space, the space themselves. And so this is the this is the pre-processing of the input vector in input text, and from there we can go to the transformer model itself. So in the transformer model, we can see that the both at the same time the input embeddings and output embeddings, both of them are processed with the positional encodings, and they're entered in the within the multi-head attentions. And on the decoder side, it enters the masked multi-head attention. So in the multi-head, after it enters the multi-head attentions, it goes through normalization process, it goes through feed forward process, and from the multi-head attention it goes and feed forward network, it goes through the multi-head attention of the decoder. And there are multiple layers or multiple blocks of attention, or multiple blocks of encoder and multiple blocks of decoder. Okay, so in order to understand transformer architecture, we need to understand the attention block first. Then we need to understand the multi-head attention, and we need to understand the mask multi-head attention, and after that we can grasp the whole concept of the transformer architecture. Uh, okay, so the key, query, and value concept is it is fast introduced in the attention is all you need, even though attention existed before this paper in from 2017. The key value query value key value concept is appropriated from the database system, where from the database management system, where we have a query, and using some with some key, we can query into the database, and we can retrieve some value from the database using the key, using the key. So after we feed the query key value vector through a linear layer, there should be linear layer here. So after we feed query key value vector through a linear layer, the queries and the keys undergo a dot product matrix multiplication to uh, to produce a score matrix. The score matrix determines how much we focus in a word that is like dependent on other words within the sentence or within the context window. So each of the word will have a score that corresponds to other words in the time step, or that particular positions within the context window. The higher the score in the genres, like the higher should be the attention to the to that particular word vector. So and okay, so if we look at the equation itself, so after the query times keys, matrix multiplications, we need to scale it with root over d of k, that is the dimension, that is the dimension of the query k values, uh, one of the dimension of the query key values, and this division is to make the gradients more stabilized, as multiplying values can have some exploding effects over many iteration of the model. So after we create do this division, and with the multiplication of query times key matrix, we're going to multiply with this with the value matrix, and we're going to do some softmax. We're going to do some softmax to the query times key value matrix. So after using the softmax, we're going to get some probability values that's going to be between 0 and 1. So okay, so after we are done multiplying the softmax, after we are done multiplying the softmax value, we'll do another matrix multiplication, but this time we will do this with the value vector. So but this what I described here, this is for single attention. This for single attention. This doesn't generalize. This doesn't generalize to. Okay, so this for single-headed attention. But what transformer did is that they parallelized the process. So instead of doing one attention at a time, we are doing here multi-headed attention with multiple into n vectors at the same time. So for the multi-head attention computation, we are going to split query key values, all of them, into n vectors before applying the self attention. So the split vectors then go through attention process separately and independently of each other. Each self attention process is called like each of them called a head, and each head produces an output vector. Output vectors, and after this whole process of after this process of attention block, each of the attention is concatenated, and they are normalized using a linear. They're normalized using some linear normalization. Okay. So like multi-head attention is a like we can so somewhat say that multi-head attention is a block in transformer network that computes the attention weights for the input, and it produces an output vector that can be understood, or that can be processed by the decoder like. Okay, so there's another concept we need to understand in order to understand the transformer architecture, that is the residual connections. So in a transformer, the output of the residual connections goes through a layer normalizations, as we can see it from here. So the normalized residual output gets projected through a pointwise feed-forward network to get for a further processing. The pointwise feed-forward network is a couple of linear layers with a like ReLU activation, or some other activation, or like 10 hyperbolic activation in between. The output of that is then added to the input of pointwise feed-forward network, and then further normalized again. So the residual connection, the residual, as I was saying earlier, that residual connection helps the network train by allowing the gradients to flow through the networks directly. The layer normalization are used to stabilize the network, which results in substantially reducing the training time necessary. The the point-wise feed-forward network try to capture all the patterns that is like spewed out of the multi-head attention layer. So in the this is the encoder block, and there's like multiple of them stacked together. Like in the transformer architecture, there are six of the encoder block, uh, and there were four of the decoder block. Or okay, so in the encoder, all these operations are done to encode the input in a continuous representation with additional information of attention and added context to each of the word embeddings, and so uh, so that the decoder can know from where to give more attention, and at the same time where to uh, and to understand and to capture the context of the whole text, whole essay more in a better way. Okay, so the decoder in the transformer architecture, it is an auto-regressive process. So that means that the next output depends on the everything that has come before it. So the decoder is in transformer architecture is to generate text sequences. The decoder looks almost closely similar to the encoder block, except for the masked multi-headed attention. So um, so the decoder is okay. So the decoder like starts with a start token, and it takes a list of previous outputs as inputs, and it takes the encoder outputs that contains the attention information about the inputs that it has taken previously. So the uh, okay, so so in the beginning, just like the encoder, in encoder, the output embedding, the decoder takes the input text as output embedding 2. So the decoder itself uses masked multi-headed attention. It is little bit different than the multi-head attentions. So most of the case, like this works similarly as multi-head attention, except for the bottom triangular of the matrix multiplication. It's a like either like bottom part of the triangular matrix multiplication of the multi-head attention. So so the reason for this is that the decoder itself is auto-regressive, and it generates the sequence word by word, and like they're like as the input text are sequential, we need to prevent it from generating future tokens. For instance, uh, like there can be sentence that I am fine, and in order to compute the attention score for the word am, we should not have access to the word fine, because the if that word feature was generated because that word is generated after I calculate after I calculate the attention for the word am. So the word am should only have access to access to itself and the words that comes before it. So uh, so in order to capture the sequential nature of it, yeah, anything like we're going to like instead of a is everything everything that is not uh, uh, everything when the multiplication happens with the q and k, it's going to be something like this. On the row wise there will be a start token, and then I am fine, three different I am fine, and on the row wise there will be start token I am fine. But when the attention score for the M is being generated or calculated, it's going to calculate the attention for I and M for the start token, but it's not going to calculate attention for M and fine, as it doesn't have the access to the feature token yet. So to do this process, the value is instead of putting the value themselves to 0, for the feature tokens it's put as minus in negative infinity, because after the softmax layer, after the softmax process, the negative infinity will be turned to 0 itself, and so they will be ignored. Okay, so just this difference makes the turns the multi-head attention to max multi-head attention. Okay, so um, um, so we can see like there's another multi-head attention after in the decoder after the fast mass multi-headed attention. So in this layer, the encoder's output are the queries and the keys, and the fast multi-head attention layer outputs are the values. So this process matches the encoder's input to the decoder's input, allowing the decoder to decide which encoder input is relevant to put a focus on. The output of the second multi-head attention goes to a point-wise feed-forward network, feed-forward layer for further processing. So from here we are finally getting the output from a transformer, from the transformer architecture. So and this output goes through a normalization, and there's a final layer that act as a classifier. There's a softmax functions that act as a classifier. The classifier classifier like predicts the classifier size is as of same as the word embedding vector. So it's like on the output, like it's going to generate it's going to decide like what is the what would be the predicted vector is by multiplying the softmax output of the softmax with a one hot vector. So the decoder takes the outputs and adds it to the list of decoder inputs and continues decoding until a token is predicted, and the highest probability prediction is the final class which is assigned to the AND token. And like just like encoder itself, decoder is stacked like n times, and each layer takes input from the encoder and the layers before it, and by stacking the layers, like the model can learn to extract and focus on different combinations of attention from its attention heads, and okay so and after taking the combination of attention from different attention heads, multi-head attentions, and by concatenating all the result, it can generalize the result instead of making and parallelize the process. So this is the transform architecture on board overview. So on the next later videos we will try to go through on different components, and we'll go through finer details.